So we've got one final little bit of integration to deal with, but this is in many ways a lot more straightforward than all of the algebraic stuff that we've done, because this is what we do when we have a function that we have no idea how to integrate algebraically, and none of our methods, the strategies that we have, work. And when you're faced with a problem like this, the only way you can really tackle it is to come up with a roughly correct answer, an approximation. And so what we really need to establish is what is a sensible way of approximating the area underneath this curve. And the clue is in the name. It's called the trapezium rule. So what we do is we draw a bunch of trapezium underneath the curve. We find their individual areas and we add them all up. And that's it. It's not particularly complicated, the idea. However, as with other numerical methods, the number crunching is a bit time consuming, and so you need to know what you're doing and how you crunch the numbers. So if we start with our curve like this, it's y equals f of x. We have literally no idea what the function is, and it doesn't really matter. What does matter is we need a function which we can determine the values of. So I need to be able to pick a point, say this one here, and work out what the value of that point is. And I need to be able to do that all the way along my curve. And as long as I can find out values of points, I can sort this method out. And I want to integrate it in between these two A and B points on the graph. And what we basically do is I just break this up into a bunch of vertical strips, something like that. Evenly spaced, unlike my doodle, but a bunch of vertical strips. And for each of these vertical strips, I sort out how wide the strip is, how tall the beginning and the end of the strip is, and then I calculate its area roughly by assuming it's a trapezium. And one thing you'll hopefully see straight away is that will not be perfect, because if I draw these lines in to turn these into trapezium, some of them are really close to being on the curve, and some of them are clearly way above and way below the curve. And maybe you can see kind of intuitively, if I have more strips, if I make these strips thinner, then I will automatically get trapezium which are closer to the actual curve. However, adding in more strips involves a significant amount more calculation. So as with most things, it's a bit of a balancing act between accuracy and the amount of work you actually have to do. Generally speaking, on exam questions, they don't give you that many strips because you need to actually have time to type it into the calculator. So you don't have to do hundreds of them. Usually it's somewhere around 5 or 6 strips because that's reasonable to do in an exam time period. So what we do is we break this thing into strips and we sort out the height and width of each strip. And I've got a handy little ... here, because although clearly we have our curve and there's roughly one more strip in there, in general, we can have any number of strips, and in general, the gap between A and B can be any sort of size. So we kind of generalize this by saying, well, we go up to yn coordinates, and what's really, really important to notice is I've got 1, 2, 3, ... n strips, but I have a point at both the A and the B. I have one extra coordinate because I need 2 for every single trapezium, but every single point's counted in 2 different trapezium except these very first and very last ones. So I go from y0 up to yn for n strips. There are n plus 1 y values, and that's really, really important. And what we do is we just work out the area of the trapezium, which hopefully you remember from GCSE is half of a plus b times the height, and in this case it's kind of upright, so the height is h and the a and the b are the 2 y values. So this trapezium, which is the first one, is in particular half of y0 and y1 multiplied by h. And the way we set this up is we split everything into equally wide trapezium. So this h value will be the same for every single one the whole way along our function. And the half is going to be the same all the way along because we're always finding a trapezium area. So the only thing that changes is the y values that we put into that calculation. So what we end up with is that the integral of my function of x between a and b is approximately equal to, not exactly because we're just approximating, but it's approximately equal to half times by h, because every term is half times h, times by, and then I do y0 plus y1, and then I do y1 plus y2, and then I do y2 plus y3, so on, until I get to yn minus 1 plus yn. And perhaps you can see already the y1 is in here twice, and y2 is in here twice. y3 will also be in here twice. In fact, all of them are in here twice up to yn minus 1. But yn and y0, the very first and the very last point, we only count once. So we can tidy this up a little bit. So this is approximately equal to half h brackets, and then I can have y0 and yn separately, and then two lots of every other term. Okay, and so we've kind of got this idea that because I can break it up into trapezium, I can switch it into a calculation where I'm doing the height of the trapezium, which is just the width of every single piece, half of that multiplied by a sum of all of these y values. And I need to count all of them twice except the very first and the very last one. And this is actually in the formula book, but in a slightly more condensed format. So in the formula book, you'll see this version, which says the integral of y dx is approximately equal to, and what they do is actually they put the y0 and the yn at the ends and the 2 in the middle. I kind of grouped my y0 and yn together, but this is the way it's written in the formula book. And basically, we just need to know how to figure out what h is, and then to plug these values in to find all your y's. And that's it. And h, it says right here, is b minus a divided by n. Well, the reason it's b minus a over n is because I'm going between a and b, and I'm splitting it into n strips. Well, the width of this whole thing is b minus a, and then I'm dividing it by n, because in this drawing I've drawn 6, so I divide by 6, and I get how wide each individual piece is. Okay, so the formula book tells you how to calculate this, but what it's actually just telling you is h is how wide each strip is. And yi equals my function of a plus ih. Again, that is a silly, complicated way of saying yi is the y value at each of these positions. You don't need to worry too much about this slightly odd way of writing that. It's just saying it's the function of a plus a little bit more depending on which strip you're working on. So you just need to remember, it's the y values. Okay, and that's it, really. It's not massively complicated. What you do need to do is get reasonably efficient at tapping all of these things into your calculator. And the next little video clip will model an example for you, including how you can speed up that calculator work reasonably well.